right, guys, we're back for another day. And Garrison just ate. Got some tired folks in there. And here, yeah, I hear you. I hear you. It's it's I don't know. It's weird to just think about like how the world is going to continue to develop and change and or go back to how it used to be. It was uh, I think we got that email, I think was it yesterday from UCR that's like, everybody gather, but masks and stuff, but maybe distance, but gather. And it was kind of like, wow, that's cool, good. We're getting there, but then it's like, so is the pandemic done? And and last night, as I say in my like introductions in my earlier classes, I grew up playing ice hockey, so we still watch ice hockey. And like last night, it was like big start of the season essentially. It was 2 days ago, but we were watching last night, and it's like first time people were in buildings in Canada since March 11th, 2020. And I was like, oh my gosh, like there's like these days that I don't know if it was that day in particular that'll like live in like infamy or whatever, but I do remember like the day that really sticks out is given that I've married into I married someone who's a big Utah Jazz fan. That first person, the first notable person in the U.S. Sports world to get COVID was the center for the Utah Jazz, and I remember just that day. So hopefully we're on the tail end of stuff. I really have no idea, but in the meantime, hopefully you guys are just staying safe and figuring out the right rhythm for you. I'm going to keep doing everything I can to make this class as engaging as possible online, knowing that there are some limitations, but then we can also, take advantage of things like the fact that everything's recorded. So, so yeah. So what's going on in this class? Where are we at today? So you guys did this lecture quiz 2. Couple things about lecture quiz 2. I got an email yesterday that was like, there might be something wrong with like the X and Y variance, and I was like, oh no. And that was exactly right. So if you did the quiz before yesterday afternoon, I've adjusted your score to account for that kind of mess up. That was totally on me. I'm taking full responsibility. So don't worry about that. The other thing is that I am fighting with Canvas left and right with when it comes to putting together quizzes, and it's really a lot clunkier than I expected it to be, and it's no fault of you guys. So what I want you guys to do is make sure if you see something that was like off or wrong, definitely feel free to reach out to me. And a few of you guys did overnight last night, and there was something with like decimal points and whatnot that were kind of wacky. And so I've put in these like additional correct answers into Canvas, and my assumption is that it should just like fix everything immediately, and it's not. But what I will do, and what I did last week as well, is I'm actually going to go through every quiz by hand, and just look at each quiz and just make sure that if you put 0.5 instead of 0.50 or 0.5 or something, you're going to get credit. So if you are concerned, don't hesitate to reach out to me, but also know that I am making sure that I'm doing my like double and triple check when all is said and done. So I'm certainly going to be on it, but if I miss, I am not above missing something too. I certainly can miss something. So so don't hesitate to reach out if you think there's something that I'm missing, because I want to make sure that everybody's getting the credit that they deserve. So all right. So we've got that aside. Lecture quiz 3 is going to be released today. I might actually I might release it one day later. It'll be due next Thursday, just like it has been. I will try to put together a lecture quiz 3 practice, just like I did before with this one, so you guys have a sense of just at least what's coming. I think this helped. And then, so lab assignment number 1 is going to be due on Saturday. Lab assignment number 2 is posted. You can see that here on our Canvas right here. So you'll be going over that on Friday or Monday, and it'll be due the following week, following Saturday. And then problem set 3 is also posted. What I want you guys to know when it comes to these problem sets is that the first problem set was like kind of long and real dense, and there's covering a lot. These other problem sets are maybe a little bit shorter. Sometimes you cover everything, sometimes you don't. I have days embedded into our whole discussion lab stuff to make sure that all the questions eventually get covered. So don't worry if you want to see them again, you'll have an opportunity to do that. So the other thing to note is that I have a kind of unmovable meeting that I have to run off to like immediately after class. So I'm not going to be around for office hours today. Shoot me an email if you need something. The other thing is a Discord was just created. So I'm on that Discord. I'm learning how to use Discord. So so I can hold office hours like on there, and we can like chat on there. We can also, if you want to meet up in another way, that's fine. But I think having office hours, maybe more office hours in another week, could be more valuable than having them today. Anyway, so I don't think. Hopefully, you guys aren't too bummed about that. But again, I'm obviously going to be around later this evening if you have to send me an email. So I don't know where the link for that is. Is somebody on that? Maybe I'll find. Hold on. I'm gonna try to find it here. Bear with me. Let's see. We'll see if I can pull this off. Yeah, I'll put it on eLearn. I just got it. So copy, paste. I think that's it. This is a big moment, guys. I just gave you the Discord link. I'm growing up, or something. so yeah, it's a good moment. Okay, so the other thing I want to do, I got a couple of requests for this. So yeah, I'm gonna adjust. I'll make sure everything's adjusted on quiz 2, just like I did with quiz 1, to make sure everybody's getting the correct amount of points that they deserve. So that'll be. I'll be doing that. Now, I did have some requests to go over the quiz, and people had different versions of the quiz. So I think the best way to really go over it is to actually go over the practice problem here, because this is an important concept, and I want you guys to know when we see these regressions, where are they coming from? So when we say, and when we look at this, and this is I botched it for those who took the quiz early. But hopefully in all the examples I use, you guys will see there's a clear independent and a clear dependent variable. And so what you see here in this practice problem is that we have SAT scores from high schoolers, right? That's when you take the SAT, and then incoming freshmen and their first year GPAs, the SAT score is going to come before the first year GPA. So there is this kind of natural time element that gives us independent and dependent variable way to think about it. Just like with the quiz, you had fertilizer and then the fruit, right? The yield of the fruit. You don't necessarily, you think about the fertilizer changing the yield as opposed to there being fruit and then fertilizer coming from somewhere, right? So the first thing that you want to do, right? So we'll just identify this as practice quiz 2. Practice quiz 2. And again, I hadn't planned on necessarily going over this, but I actually thought this is important. So it's a nice kind of segue into just the rest of the stuff that we're going to do today. So practice quiz number 2 is saying we've got 2 variables, right? And so start like this. We've got 2 variables. We've got SAT scores, and we'll say first year, we'll say UCR GPAs. Okay, so I do something like that. I like kind of just making it something that we can, something tractable, something familiar, something comfortable. Okay, so that's going to be our 2 variables, and then we need to ask ourselves, well, which one is the dependent variable, which one is the independent variable, which one is just kind of moving, and then which one is determined by that moving variable to some degree. And in this case, we would say that the SAT scores are independent, right? Because again, from a timing perspective, right, you're taking the SAT scores first, and then you have some sort of first year GPA. So these first year GPAs are going to be our dependent variable. So our independent XI, dependent YI, right here. Okay, so that's first, right? That's our first thing right there. And then, right, we've got some other information, right? We've got some other information that'll help us get to this particular answer. But the first thing you would want to do is actually write out the regression. Okay, we're trying to get regression coefficients, right? So a regression is going to be the GPA of each individual student is equal to beta 0 plus beta 1 SAT I, okay? And we're gonna go ahead and put a hat on here, like this is like the prediction, right? This is what we're predicting. But we could say, all right, well, this is like beta 0 and beta 1. We'd like to know what those values are. We're gonna end up just predicting them though, okay? So here, right, I'm saying right now, these are the actual estimates right here, right? But, right, even though those are the actual estimates, right, we can only calculate predicted values, okay? So this is an aside. This is not necessarily what you were thinking about when you were going through the quiz, but I do want you to have that in the back of your mind as we move forward here, okay? All right. So what are the coefficients of an OLS regression given all this information we have here? So what is the information that you're given? Well, first you're given the total students. So those are your number of observations, right? We've got GPAs for each student. We've got 1,000 students. We've got the sum of both the GPA, which is equal to the sum of XI, which is equal to 3,172. Okay. Then we've got the sum of all the SAT scores, which is going to be the sum. Oh, sorry, I got that backwards again. Cole's probably sitting there saying like, oh, I screwed that up again. I did. So got that backwards. Sorry about that. So I'm going to highlight this. There. I cannot mess this up now. There we go. I guess it highlights how easy it is to do that. So, okay, so I tell you what the sum of the XI is, the SAT scores, 1,002,041,000. There we go. Okay. All right. So we've got our sum of X, we've got our sum of Y, we've got our N. Right. One of the things, why am I doing this right off the bat? Well, I'm doing this right off the bat because we can actually get our Y bar and our X bar. So our Y bar will just be 1 over N times the sum of YI, 1 over 1,000 times 3,172, 3.172. Okay. Then our X bar, this is going to be 1 over N times the sum of XI, which is going to be 1 over 1,000 times 1,241,000, and then we're done. So this is going to be 1,241 is that average SAT score. Okay. All right. So we got Y bar, we've got X bar. Why would I even go about doing this? Well, I go about doing this because our beta 0 hat estimate is going to be equal to that Y bar, 3.172, minus beta 1 hat times our X bar, right, 1,241. And actually, let me get rid of this. I'll get rid of that comma there, just to make sure it's like we got 1,241 versus 3.172. Okay, we've got to figure out beta 1 hat though before we go on any further. I kind of lay that out for you. So we've got the covariance, all right, of our SATs and our GPA, right? I've given you that. That's 10,000 right there. And then this is divided by the variance of our X variable, our independent variable. So in this case, this is going to be SATs. Okay, so we've got 10,000 divided by 2,500,000, right? And so these are big numbers, but again, it should be, you can kind of cancel things out pretty quickly, right? You're left with that. This beta 1 hat is just simply equal to 1 over 250, which is 0.004. Boy, that kind of came quick, right? So you start to say like, all right, we've got all these numbers floating around, but like when it comes down to it, gosh, it's just, I would give you easy numbers to calculate this, right? You just got 1 over 250 or 0.004. Okay, we're gonna figure out kind of that interpretation in just a second, but before we do that, right, let's get that beta 0 hat, which is gonna be equal to Y bar, which is gonna be 3.172 minus 0.004 times X bar, which is 1,241. Okay, and actually I'm going to write that better. You guys probably have a better look too, so it's more important to make sure this looks good here. Beta 0 hat is equal to 3.172, our Y bar, minus 0.004 times our x bar 1,241. Okay. When we do this calculation, we end up with beta 0 equal to, what do we got here? I wrote this down. Oh, negative 1.792. Okay, 1.792 negative. Okay, so, right, I've got two questions there, right? What are the coefficients of the Ols regression? Interpret the coefficients. Do they make sense? Okay, so let's do that, right? I got some extra stuff here. I'm going to move this down. I'm just like writing big now. So there we go. Move this down to there. Okay, so let's start with beta 1. Right, I think that's a natural interpretation there. I think it makes sense. Okay, and this will help us, I think, just understanding regressions more broadly. Beta 1 is 0.004. Okay, so this is saying a 1 unit increase in our x variable. All right, notice how I'm gonna write this very general right now, and then maybe then get to more specifics in just a second. A 1 unit increase in our x variable is associated with a 0.004 increase in our y variable. What are we missing? Don't forget on average, right? I got that. I'm gonna have an exclamation point there because like that's important, right? Don't forget that on average, okay? All right, so we can kind of look at this very broadly. That's what all of our beta 1s will be. We can say every unit increase in our x variable, right? X1 variable in this case, that's going to increase our y variable by 0.004 on average. Does that make sense? Like, is that how we want to think of SAT scores going from like 1,241 to 1,242? Here's what I like to do when you have something like this. What makes more sense in terms of an SAT score difference, right? You don't sit there, when you guys were taking your SATs, you weren't like, oh, it went up, 1 point, I'm so happy, because it doesn't go up by 1 point, it goes up by 10 points. But even then, you weren't like, oh, I went from 1240 to 1250, right? I think kind of a better way to think about this interpretation is what happens when we have an increase. Let's have an increase in our SAT score, our x variable, equal or of 100 points. So that means that our change in x is equal to 100. Okay, our change in x is equal to 100. So now our SAT score goes up 100 points. What do we expect our GPA to go up by in that following year for first-year freshmen? Well, all we have to do is say the change in our y is going to be equal to beta 1 times our change in x. So this will be 0.004. For every point that we increase our SAT, going to increase that GPA by 0.004. Multiply this by 100. This ends up being 0.4. Okay. So then, right, instead of having this kind of like awkward 1 unit interpretation, we could say for every 100 point increase in SAT scores of a student, we expect the GPA to increase by 0.4 points on average, right? So then when we think about that interpretation, does that interpretation make more sense, or can we say that the coefficient that we get makes more sense? I think it does, right? I think it's easier to think about our regression in that way because now we're not saying there's these like 1 unit changes in our SAT score, but yeah, like somebody who gets a 100-point increase on their SAT scores, right? We think about those individuals going from 1,200 to 1,300 to 1,400. The average GPA is going up by 0.4, right? As opposed to 0.004. Okay, so one class is kind of going, each class on average is going from like, a B plus to an A minus or a B to a B plus or something like that. Okay. All right. So that's our interpretation of beta 1 hat. And I'm going over this slowly because I know that a lot of people are kind of like, I don't want anyone to kind of fall behind or get lost in the weeds or anything like that. So it's nice to kind of just say, okay, this is a nice, clean interpretation of beta 1 hat. And you might have done it and thought about it already, but you're kind of seeing it maybe in a different way. And that's what we want. We want to have all these different ways of thinking about this. Okay. All right. So then what about beta 0 hat? And I had a great email about this because someone was looking at the question on problem set 2 and interpreting the beta 0 hat there. So the beta 0 is negative 1.792. Okay. So what is this saying? And again, let's do this in a general case here. There we go. Right, a general case here. Get rid of that. We would say that when our x values equal 0, right? All of our x's equal 0, right? We expect our y variable to be negative 1.792 on average. So is this a reasonable number? Well, here's the thing you want to ask yourself before that is, should you even care? Right? Should you even care that our beta 0 is negative 1.792? And the reason I can say that is you have to really say, does it matter that x equals 0? And in this case, we would say when x equals 0, right, this means that our SAT score is equal to 0. Well, if SAT scores are required, this seems like an impossible observation, which is essentially what we can think of it as. The same thing as student-teacher ratios being equal to 0. But our SAT score is equal to 0, right? This is, you can almost think of, I guess it's not, it is impossible. Isn't like the lowest score 400? Like, so, you're not, if you take the SAT, you're not going to get 0, you're going to get 400 at the lowest if you miss everything. Right, so this score is not part of the range of SATs, not in the range, right? And so then, so because this is impossible, right, we can think of beta 0 hat is and I'm going to put in quotations, a leveler of the regression line such that it ensures that the regression line includes, includes x bar, y bar. Okay, that's what it's doing, right? So it's no longer something that we need to interpret. It's simply saying, look, we found the right slope. Now we just need to make sure we've got this slope of 0.04. Now we're just setting the line up so it goes through this x bar, y bar, right? That's the step-by-step process. Okay, so when we have a beta 0 of negative 1.792, that's like saying, hey, are you a student at UCR? Did you take the SAT? No. Well, your GPA is worse than an F. It's like it has no meaning, right? So if it has no meaning, that's fine. It just means that the beta 0 is a leveler. Okay. So So hopefully that's helping just kind of general regressions, especially when we go back to our student-teacher ratio test score regression. Right, we can kind of start to say, that's what this is all. We can see the meaning in just a more complete way. Now, the last part of this, though, okay, the last part of this is figuring out how do we predict values of y. Right, let's predict values of y with values of x. Right, so I say in this case, right, we've got an SAT score equal to 1,000. What do we expect the GPA to be? So we would say GPA hat is going to be equal to negative 1.792 plus beta 1 times 1,000. Okay, So when we do this, when we have somebody who we look at the group of students that have an SAT score of 1,000, what do we expect their GPA to be as a first year student? We expect about a 2.208, right? A 2.208, right? Does this mean that every student gets a 2.208 if they got a 1,000 on the SAT? No, absolutely not, right? That's just the average, right? That's just the average SAT or GPA for that SAT score, right? Given our regression. If we look at individuals who got, was it 1,200 next, right? How do we calculate this prediction? Well, we've got that negative 1.792, but now instead of multiplying by 1,000, we multiply by 1,200, and we end up with, what do we got here? 3.008. Right, so if we look at the students with a 1,200 SAT, they seem to get around a 3.0 on average, right? Doesn't mean that you can't get a 4.0 or a 2.0 if you got a 1,200 SAT. But then when things get a little weird is out here at 1,600. So when we predict our GPA for students who have a perfect SAT score, right? What do we expect their GPA to be? We expect it to be 4.6008 or 4.68. There we go. Right? Well, that certainly doesn't make any sense, right? So we look at those individuals and with an SAT of 1,600, that's the average. Well, what we have to remember is that when we look at a data set, right, what values of X are actually in the data set? This may be a data set that just doesn't really have any SAT scores of 1,600, or there may be like one, right? And we're fitting the line as best we can, and that's what we have this prediction of 4.6, but obviously that's not going to be your first year GPA. So again, what this is highlighting here is that when you run a regression, you can go ahead and get like interesting or valuable coefficients, right? But it's not necessarily true that those coefficients are going to always lead to meaningful outcomes or predictions, right? So we have to just have these caveats and say, maybe saying the SAT equal to 1,600 isn't that different than saying the SAT score is equal to 0 and we have a negative GPA, right? There's just not that many observations or any out there. So we have to make sure that when we look at these predictions, we're only putting any weight on those predictions where our X value is actually, it actually exists in our data set. So yeah, do we have people with SATs of 1,000, 1,200, 1,400? Yeah, sure. But then once we get a little too high, yeah, we essentially go above what that barrier is for our Y value, right? So hopefully, right, and again, this was like a last minute thing for me. I hadn't planned on necessarily talking about this, but I think that this is really the crux of like the entire term, right? We really want to make sure we feel good about this. And so if you didn't do well on the quiz or in terms of like, let's say that you ended up doing okay, but didn't understand it as well as you'd like, make sure you go through it. If you didn't do well, make sure you go through, kind of walk through it step by step. And if you have questions, definitely come and reach out to me. Question came up, wouldn't it be more realistic to ask how GPA affects SAT scores? That depends on which GPA we're talking about, right? So if we're talking about like high school GPA and SAT scores, maybe that's going to be that's going to be a different direction, right? Because what you do in high school is going to be maybe more relevant to the SAT than maybe the SAT does to college. So yeah. So any questions or thoughts on that? Hopefully that felt good. Hopefully it felt like nice to just see that again, right? And like I said, it was kind of a nice, we'll say, continuation of what we did last class. Because if you remember last class, we went through that detailed derivation. It was kind of painful. I got it. But then we started thinking about the R squared, and so we got this R squared of 5%, and you can start to see how that's describing our variation in our Y, in this case test scores, but you could think of it as GPAs as well. So yeah. So if you've got questions just on kind of that fundamental stuff, let me know. We're going to keep talking about it, right? We're not going to just say like, okay, we're moving on from the basics of, the kind of the basic foundations of regression. Good luck. Right, we're going to keep walking through this, but we're going to kind of have maybe a slightly different angle than just interpretation. Okay. All right. So if there's no questions, right, let's talk about what we did last class and where we're headed. Okay. So last class, right, I talked about the R squared, and I think the R squared, everybody loves the R squared. And the reason everybody loves the R squared is because it seems so clear. Like it's like one of the few things that just seem to like not like go in circles, right? It's just saying like, how much of the regression do we explain? Like, is it 5% or is it 100%, right? Or is it somewhere in between there? And you can kind of have this clear indication of what this R squared means, and it's the exact same meaning regardless of the regression, right? The R squared is telling you that fraction of the variation in your outcome that you're explaining. It doesn't change regardless of your X's or your Y's, okay? Now, what we have to be careful of, though, is that you'll get into stata and all this stuff, and you will want to just run regressions and get the highest R squared you can. And, it's a rite of passage. It's cool. Like, go ahead and do it. However, when you're actually thinking about regressions, you don't want to just say, let me just put in every variable and get as high R squared as I can, because that's actually not a, well, there's lots of reasons not to do that. We'll talk a little bit about the adjusted R squared down the line, definitely 108. But it also is kind of, you end up losing significance between your variables. That's what we're going to talk about a little bit more. To start that off and to get really where that comes from is, instead of asking ourselves like, hey, how much of this variation in test score do we explain? We really want to know, does X actually cause a change in Y? Right? Does it? So it's like, we can explain all the test score variation we want, but if we can't actually say if it's because of student-teacher ratio, we haven't learned what we really set out to learn. Okay. So in order to answer this question, is does X actually cause a change in Y, we have to make some assumptions about the regression model. And it's funny because I think, when you hear like, let's make some assumptions, it really sounds like off-putting, right? But actually, this is going to tell us a lot about relationships between X and Y, and kind of the underlying meaning of regressions. And it's really, really, I think, a valuable thing. Okay. So say like this: can we believe our regression results? Okay. So what I'm going to say, that the kind of short answer to this is that if assumptions, what I'm going to say are 1, number 2, and number 3 hold, these must hold actually. These must hold to believe our results, okay? And what do we mean by believe? That the beta 1 hat estimate is meaningful and accurate. Okay, we'll get into some other language as we move forward, right? But that's kind of what we're saying here. So the question then becomes, well, what are the assumptions, right? And so the first assumption, right, is kind of the big one, and we're going to spend a lot of time on it here. All right, the first assumption of our OLS regressions, right? The first assumption is that the conditional mean, well, actually, starting before that, conditional expectation, right? Conditional expectation of UI given xi is 0. Okay. Conditional mean or conditional expectation of UI given xi is 0. So and the reason I keep saying conditional mean is because often you'll see or hear the phrase, the conditional mean is 0. So there's a little bit of brevity sometimes when we're talking about this first and kind of major OLS assumption. Okay, so the conditional mean is 0. So how do we write this? How do we think about this? Well, we can say that the expectation of UI given xi, right? That's what we have here. Expectation UI xi. This is equal to 0. So given we know the value of xi, the expected error is 0. Right, so that's like, again, we're really beating up this conditional expectation here, right? And we have it drawn up here, and the drawing up there is hard to interpret right now, and I don't need you guys to think that much about it, right? But we're saying, look, if I tell you the value of x, if I tell you the student-teacher ratio is 15, and then you look at the errors and you look at the structure of the errors, right? You'd say, the average looks to be 0. Okay, well, let's go to 20. What does it look like? It looks to be 0. What about 25? It looks to be 0. So that's really like the first pass at this assumption, right? Some alternatives, right? Some alternative definitions, or what comes out of this, right? What comes out of this assumption is that, okay, well, we've got the expected value of ui given xi is equal to 0. When we calculated or constructed these regression lines, what was the expected value of ui? Do you remember that? So it was like in the middle embedded of all those first order conditions, right? So those first order conditions, they're just like, there's so much stuff going on there. But at one point, remember, we had the sum of yi minus beta 0 minus beta 1 xi, that had to be equal to 0, right? So that was just saying, look, the sum of ui also had to be equal to 0, right? Why do I put that up there, right? And so I can put in the side here that we had the sum of yi minus beta 0 minus beta 1 xi equals 0, right? So that's kind of bringing that back. And again, I wasn't like saying you guys should remember that exact line, right? But that's you kind of remember that coming up maybe to some degree at some point in our discussion on Tuesday. Okay, so we've got the expected value of ui equaling 0. That's how we've calculated these regression coefficients. Then we've got the expected value of ui given xi equaling 0. So that means the expected value of ui given xi, which is 0, is also equal to the expected value of ui, because that's 0. So what does this mean about u and I? Right, so expected value of u is always going to be 0 in our regression coefficients, right, or Ols regression coefficients, right? We're assuming that ui and ui given xi is also equal to 0. This means, right, this has an implication that ui and xi are independent, right? So if we remember that just in that stats review, right, when we had that expected value, the expected value of x given y is equal to the expected value of x, that means x and y are independent. Here we've got the same exact thing, okay? So now more meaningfully, this is telling us that if we learn, right, learning about xi does not provide information about ui. In other words, xi and ui are unrelated. Okay. So that's what this assumption is saying. So by making this assumption, and again, kind of go back and say, all right, well, so the conditional mean is 0. That means that xi and ui are unrelated. We have to really ask ourselves, is that the case, right? Is that the case? And I'll let you guys kind of answer this over time, right? I've got this up here, and you can kind of, we're going to really dig into this, right? But let's go back to our example of class size and test scores. All right, so first, if we're going to think about this, right, we need to ask ourselves, do we think that our main independent variable, xi, is that going to be related to elements of that error term, right? Two elements of that error term, right? So how do we even get at that, right? So first, right, we're going to define our x variable, xi, which we know is student-teacher ratio or class size. Okay, so we've got class size here. Okay, so class size is going to be our xi, right? And then we need to think about what are the possible elements of ui. So here's what's really kind of a, again, it's a hard thing to wrap our head around, I think, when we're at this stage. But possible elements of UI, note, we don't ever know exactly what is in UI, right? This is unobservable, right? Like what is causing an error, we don't actually know what goes in there, but there's certainly elements of UI that we could start to back out or start to think would be relevant. So if we think about what we talked about way back in a couple weeks ago when we were talking about this example, we said, well, what goes into this error term? Well, one of the things that could go into this error term would be school resources. And that's what we're going to hit on, right? We're going to hit on school resources as kind of like our main element of UI, just because it makes it tractable, right? But that doesn't mean that we couldn't have, we'll say, parental resources or parental or household resources, okay? And then there could also be a random element. So where am I getting these things, right? So that's kind of the thing you need to ask yourself, because again, you're not given, when you come up with your own regression, you're the one that's determining what your outcome variable is. So in our case here, right, we're saying the elements of UI are, we'll say, characteristics other than student-teacher ratio that could influence our test score. Right, that's really what our UI is telling us, right? That's what it is capturing. Okay, so we've got school resources, right? We've got parental or household resources, and we've got a random element. That covers a large portion of things. Doesn't cover all of them, but I think that's a good set of categories, right? That are saying, look, we've got a test score. We're explaining some of that variation by the class size. But there's also school resources, that's part of that error term. There's also household characteristics, that's part of that error term for the average household. And then there's some sort of random element that's causing that change as well. Okay, so we've got our UIs, we've got our XIs. If, right, this is where it all kind of comes together with like essentially the violation of the assumption. If any element of UI is related to XI, that means that we violate assumption 1, and we cannot rely on our estimate of beta 1 hat. Okay. Gosh, that's heavy. It's heavy stuff, right? So we got like this is like dropping the hammer here, right? So we define what our XI is. We think about what our UI is. So these are going to be the characteristics that influence our outcome that is in our X. If there's anything in those characteristics that are related to X, we violated assumption 1. So the question then becomes like, wait, so is it always related? And like, what is the nature of this relationship, or of this violation of this, X and UI relationship? This is where it gets really complicated. But I think it's where we're really separating or parsing out this idea of causation versus some sort of correlation between just X and Y. So what I want you to do here is I want to show you what a violation of assumption 1 looks like. And your answers are coming up essentially exactly like I was hoping for. Okay, so what I'm going to do, right, and this is what I'm going to do throughout the term, and it's something that you want to do from kind of all angles, but I'm going to assume that there is a dominant element or characteristic of UI, right? Because if you start to think about what can go into UI, like what can influence test scores, it's like everything. Right? So we can't list out everything, right? But what we can do is we can say, okay, well, like what's like a dominant element of UI? Like what could possibly influence the test score more than other things? And what you guys said early in the term was teacher quality, right? You guys kept saying, oh, I think teacher quality matters a lot, okay? So then, right, we need to ask ourselves, do we think that there's a relationship between the average size of a class and the types of teachers that are teaching in those classes, right? So this is our assumption. So no, we could assume it could have been anything, right? It could have been parent characteristics, something like that, right? But we'll just stick with teacher quality again to not make it so cumbersome, okay? So, right, we need to ask ourselves, is there a possible relationship between the size, we'll say the average size of a class and teacher quality, right? In other words, do higher quality teachers go to small class districts? That's really the question, right? And that does deserve a highlight, right? That does deserve a highlight for me, right? Because it's saying, look, if we are going to have this relationship between U and XI, and we're assuming teacher quality is like the driving element of our UI, there's an issue if we say yes to this question. This is the question we need to answer yes or no to. Do these high quality teachers go to small class districts? Okay. So if this is the case, the way that this would play out is that in we'll say high student teacher ratio districts. Oh boy, losing that. There we go. Right, in high student teacher ratio districts, right, they attract low quality teachers, right? And the story that you would tell, right, and you're just telling a story here, you don't have any data to back this up necessarily right now because we don't really know how to measure quality, right? But we would say, oh, if you're a high quality teacher, or it's, in this case, a low quality teacher, you don't have like the ability to go exactly where you want. So we assume that teachers like working in smaller classrooms because they can connect with students better, maybe, right? So in low student teacher ratio districts, right, the way that they would attract high quality teachers is they would say, hey, your class size is only 20 as opposed to 30, right? So it's a lot less than what you're used to, and you're going to be able to do a lot more things that you've been wanting to do, okay? So, right, and it's funny that I say this because the start of my career, I was at a low student teacher ratio university, Xavier University, a small liberal arts school, and now I'm clearly in a high student teacher ratio university. So maybe I've just become a low quality teacher. I'm not sure. So it's, again, you have to take it all with a grain of salt, and changing answers. Oh, geez. So let's see this play out, though. Right? Let's see this play out visually. That's kind of the goal with this underlying class size teacher quality relationship. Okay. So we've got the regression test score equal to beta 0 plus beta 1 student teacher ratio I plus UI. I think it's fair because we've seen it before. We can assume that beta 1 is less than 0 and that UI is represented by teacher quality. Okay, by teacher quality. Okay, that's what's driving the error term. So now when we were to graph this hypothetical relationship here, right, we can go ahead and put our graph up here. We've got student teacher ratio here, we've got test score here, and we've got our downward sloping line here. Okay, so we've got beta 0 plus beta 1 student-teacher ratio, okay? And so let's put some data up there, right? Let's put some predictions up there. So if we're in a low student-teacher ratio district, right, we predict this point right here, we predict a fairly high test score, okay, Y high, okay? However, right, in these low student-teacher ratio districts, what's going on? Well, we have high teacher quality driving our error term. So it's a low student-teacher ratio district. That makes the test score high. But then when we actually think about what's going on with the error term, now those errors are more likely to be positive than they are negative. Because we're saying, oh, yeah, student-teacher ratio matters. There's also these errors. But notice the way I've drawn this is that the expected value of U given the student-teacher ratio is low is greater than 0. Greater than 0. Okay? So again, take a moment and just think about the process. Right? Think about the process here. We are in a low student-teacher ratio district. We predict a high test score, but then we would also kind of expect these districts to attract high-quality teachers. So that's going to bump up that error term, push those test scores up, right? So our error is going to be more likely to be positive, because not only do we have low or small classes, we have high-quality teachers. But then when we go over to these high student-teacher ratio districts, well, yes, we would predict this value, Y low, for our test score, right? That's what we predict that low test score there. But then we also have low teacher quality as well. So we're sitting there saying, yeah, we predict this low student-teacher ratio, but actually, or this low test score in these high student-teacher ratio districts, but this teacher quality, gosh, that seems like all these low quality teachers are going to these districts with lots of students. So it turns out that the expected value of U, given student-teacher ratio is high, is less than 0. Okay. So if you're kind of sitting there saying like, okay, this is like kind of different than I expected. I thought when we were talking about assumptions, I didn't think we were going this direction, right? So if you're kind of sitting here saying like, so does this mean that as we increase our student-teacher ratio, right, we're capturing the increase in the student-teacher ratio, but then we're also capturing the change in teacher quality? That's exactly what's happening, right? That's exactly what's happening. So to summarize just this picture, just this part, right? If the student-teacher ratio is low, we predict, we'll say Y high hat, but the high teacher quality pushes up, right? We're going to literally think of it as pushing it up. This high teacher quality, right, is pushing up test scores, right? Beyond the prediction, right? We have the prediction of Y high, but we're actually pushing up beyond that because, yeah, low student-teacher ratios might matter, but that high-quality teacher is pushing it up even more, right? Conversely, if that student-teacher ratio is high, yeah, we're going to predict Y hat low, but the low-quality teaching is bringing down our test score. All right, so I'll put a line here just to distinguish those 2 points. There we go. Right, so we've got those two kind of opposite ends of the spectrum here. All right, so taking this together, right, what we're seeing here and what we've made this assumption here, and like I said, I didn't even tell you initially on this question, whether the elements of UI are what they are, what we expect them to be, but I just said, how do you think that they're correlated? Well, this is where it really comes out here, right? The answer to this question. So what I've done is I've just said, hey, small classes, they're attracting high quality teachers. Big classes, they're attracting low quality teachers. Okay. So to summarize what's happening, as our student teacher ratio increases, the expected value of U, right, our error term, is going from positive to negative, right? It's going from positive to negative. So this is decreasing, right? So in other words, xi goes up, ui goes down. So what does this mean? This means that the correlation between xi and ui is going to be negative. Okay. Now, if we want to say this kind of more casually, right? Is there something in our UI that's related to our xi in a very systematic way? If so, right, this means that parts of UI are it's a dance with where I want the graph to be. So I'm just going to back it up a little bit, right? So parts of UI are influencing the slope beta 1 hat, right? So what we're doing with this, when this correlation exists, is that beta 1 hat is saying not only do we have this change in student-teacher ratio, we also have this change in teacher quality, right? So beta 1 hat includes changes in student-teacher ratio and teacher quality, right? And teacher quality. So what that ultimately means is that our beta 1 hat is biased, right? Beta 1 hat is biased, okay? And so what that, we'll talk more about what that means, right? But ultimately, right, what it means is that the expected value of beta 1 hat is not equal to the true beta 1, right? It's the true beta 1, the true effect of student-teacher ratios is a certain value, right? That should lead to a certain set of beta 1 hats. But if we have beta 1 hat capturing student-teacher ratio and teacher quality, it's going to make that beta 1 value or beta 1 hat value not be centered around the true value, right? So this is our true value, our true effect of student-teacher ratio. This right here is our estimated effect. Okay. Okay. So what usually happens here, right, is that people just say, okay, you get this, you move on, we're good. Okay. But I don't want to do that quite yet, right? I don't want to do that quite yet. What I want to do is I really want to talk about I don't want to just talk about the bad stuff, right? I don't want to talk about this violation because it's hard to say, hey, let's assume this. Let me show you what happens when it's not being assumed. And I'll talk more about the bias as we get going. We're going to have like a whole day and a half on that because you want to kind of know what the implications of that are, right? But let's ask the question, when is assumption 1 not violated? Okay. So I was like racking my brain about this the other day. I was like, what example can I give them such that assumption 1 is not violated? Because what it's saying is that the expected value of U given x is low should equal 0. The expected value of U given x equals middle, that should equal 0. Expected value of U given x is high should also equal 0. Right? X equals high is equal to 0. Right? So again, I ultimately need an x and a y such that, right, our ui and xi are unrelated. So a way to say this is that our unobserved determinants of yi, this is going to be our error term, right? Like what we don't observe, right? Those determinants that of our yi that we can't see, that's going to be our error term, right, are not related to whatever our independent variable is. And I said, okay, I can do this. All right, I can do this. And I said, all right, let's look at Disneyland tickets on day I as a function of precipitation on day I plus ui. Okay. I said, okay, so work with me here. Oh, I can scroll back up. Yeah. So work with me here, right? But our xi here, right? Our xi here is, we can think about the amount of rain on a day, right? The amount of rain on day I. Okay. What are some possible things? This is just because I want to make sure that you know that it's a zero. Good question. No, it's a good question. I'll just be consistent here. So it's always going to be a zero when it's through there. So, okay, so then, right, we need to ask ourselves, what determines the amount of Disneyland tickets sold? Right? Why would, and this should have been a question I asked on Poll Everywhere, but you guys can like shout it out on chat. Right? Why do you go to Disneyland? Why do more people go to Disneyland some days and not others? What's like the most obvious one? When is it busiest?
Sunny.
Sunny?
And weekends.
Okay, so we're day of the week. Okay. Now we've got weather in there. We can kind of think of it that way, right? Okay, so breaks, right? Stuff like that. So kind of days, right? But then within like a given week, right? The day of the week matters, right? But then what else? What else? There's break times. I kind of think of that as like holidays, right? And like holiday specials. Are they doing like Halloween again there now? Like it's like Fright Night or something? I don't know. Maybe I'm thinking of like Not Scary Farm or something. What, you guys get the point, right? What about the new rides, right? What about different marketing campaigns? Okay, yeah. So we've got all of these things that are influencing our Disneyland tickets. Thanks for shouting that out, Ben. Yeah, if you guys got anything else, there's so many different things that can influence Disneyland tickets, right? Now, when you start to think about it, right? But then when we think about like, okay, do we expect that precipitation to be related to like the day of the week or like new rides or marketing campaigns? It's like maybe it's like a stretch though, right? It doesn't feel quite the same as our student teacher ratio and our class size or at our teacher quality here, right? So if we were to draw this out, right, and we were to just graph this out, and I'm going to give myself a little bit more space because there's a break there, right? So we can graph this out here, and we can just say, I'll just say the rain on day I and tickets on day I, right? Well, we would expect a downward sloping relationship, right, a negative relationship. As it rains, right, we're going to have fewer tickets, right? So especially from local folks, right? So we would have beta 1 hat that we would estimate to be less than 0, right? So it rains more, right? It rains more. People are not going to say like, oh, today's the day I'm going to go, right? They're going to wait till it's a little bit nicer. And Ben hit on the head with being sunny. That's exactly what we're saying here. But then when we look at high or at low precipitation days, like low rain days, what do we expect the error structure to be? Like, do we say like, oh, well, it's definitely going to be like, there's definitely going to be some sort of positive or negative error? Let's just go with like day of the week. Like, let's say that that's like kind of the thing that determines like ticket sales that other than rain, right? Well, if that's the case, like, well, if it rains on like a Saturday, well, then we'll be above, or doesn't rain on a Saturday, it'll be above what we expect. If it's like a Wednesday, it'll be lower, and then Friday, Thursday, Monday, right? Something like that, right? We don't necessarily expect there to be a relationship or any type of like bias one way or the other. Same thing like on high rain days, right? A way to think about it, if we think about like how this could like, if it feels absurd, then it's like, it's absurd, okay? So the idea would be like, hey, it's raining today. We expected there to be this many tickets. it must be a Tuesday? That doesn't make any sense. Like if it's a Tuesday and it's rainy, there's going to be hardly anybody there. If it's a Friday, yeah, or if it's like, July 4th or something like that, right? Well, we can go ahead and see, we would imagine, right, that this is completely unrelated, the weather, to the day of the week. The day of the weather doesn't operate like that, or the weather doesn't operate on the day of the week, right? So in both of these cases, the expected value of U given no rain is equal to 0, and the expected value of U given rain is equal to 0, okay? So in this case, we would say the expected value of U given our, there we go, U given rain is 0, and the expected value of U is equal to 0, right? Those two things. That would mean that U and our precipitation variable are uncorrelated, right? And assumption 1 holds, okay? So when we get this coefficient of beta 1 hat, that's telling us that's really just capturing the rain, right? Just capturing this random rain element, right? And kind of and again, there might be holes in this. This is a really hard thing to find, but hopefully you're kind of saying like, yeah, I can see how this is different than like teacher quality, right? It's not like we have like Fridays are gravitating towards high rainy days, right? That's not the case. There's not this systematic relationship between day of week and the amount of rain. And if you want to think about this on like a given year, right? It's not like new rides occur during droughts versus not droughts. Like that's not how it operates. So that precipitation is ultimately random. So if we step back on our slides for just a second, right? Hopefully what you're saying is like, okay, so now I see what that's telling us. It's telling us that look, the distribution of our error term, right? This is the distribution of UI when there's no rain versus when there is rain, right, are both centered around 0. And that's exactly what this is saying. So the distribution of our error terms, right, when x is 15, 20, 25, it all looks the same, okay? And when we see that, when we have that, that means assumption 1 holds. And ultimately, this is going to mean that the expected value of beta 1 hat is centered around the true beta 1, given some additional assumptions about, we'll get to those next time. So I think this is a good place to stop. If I'm going to go the other direction, and I'm going to maybe leave this to you guys so we can talk about it first thing on Tuesday. But what we're going to essentially get at here is, or what I'm going to ask you guys is, can you come up with an example of a regression where the correlation between x and u is positive, but beta 1 hat is negative, or the correlation between x and u is negative, but beta 1 hat is positive. Okay? So I have an example that I'm going to share with you guys on Tuesday afternoon. But like I said, I'll let you guys go. Don't say that I didn't give you the 10 minutes back that I've kind of accumulated throughout the term with the 1 minute extra per day. So I'll leave it at that as opposed to rushing through stuff, and we'll talk about this on Tuesday. So if you got questions, stick around. Hello?
Professor, I have a question.
Yeah, go ahead, Brittany.
Hi, I'm so sorry. I was wondering, can you explain like what regression is, like, so that way I can come up with the correct example? Because I understand some of the concepts, but I don't understand everything.
So what we can think about with the example will be essentially come up or choose a y variable and a dependent variable, some sort of outcome, and something that could influence that outcome, right? And an x variable, right? So this would be an independent variable that could influence that outcome, right? And again, it can be anything. It really can be anything in terms of two variables that could potentially be related. So as somebody who like watches sports, one of the things, and I talked to my buddy about like fantasy football, and he was talking about quarterbacks. And if you watch sports, what you see often is that when a team is losing badly, like their quarterback throws a bunch of passes, so they get a bunch of points. So it's like if you were to want to run a regression on like the number of wins somebody has and the number of yards they throw, it seems like it'd be like you could run that regression, right? And you could talk about there's right. So that might resonate with folks. Another thing could be something about healthcare costs is one of the examples on your problem set. So healthcare costs and calories, or healthcare costs and exercise. That could be another example. So a regression, though, is ultimately just fitting the data. Okay, the regression is fitting the data with a line. Right, that's what it is. So if you want me to summarize like what a regression is in like a single term, we are just getting a line of best fit. You get all the data you can, and then you just say, all right, can we actually fit this data? Can we fit this relationship with a straight line, and how well do we do it? So
okay, so
yeah, go ahead.
So
keep going.
If I reiterate to like what you're saying, so it's just so I can make sure I understand.
Yeah. Please.
So a regression is pretty much taking two variables, and then creating a relationship or seeing if there is a relationship or correlation with it. So it has nothing to do with, well, I guess it does have something to do with whether it's indirect or direct.
Yep.
Or are we calculating that as well?
We're kind of getting at it with this. So in this case, like, we're seeing that rain matters, and that's like a direct relationship on tickets. Here, we're not sure that student-teacher ratio matters. It might be teacher quality that matters more than student-teacher ratio. And that's what we're going to get at. Like it depends on the regression. So with that indirect versus direct relationship. But I like the way that you're thinking about that, because that's really what we want to do. Is X directly causing Y to change, or is there some other path that it's taking?
Okay, thank you so much. I appreciate it.
No, anytime. And I apologize that I got to run from office hours, but it's not like I'm not going away. So if you guys have questions, just shoot me an email. I'll stop by on Discord and we can chat away on there. And we can just kind of keep this going. So,
okay.
Yeah. Thank you so much.
Thank you. Have a good day.
Professor,
we'll see you guys.
Can we still take the quiz?
Unfortunately, especially because I went over it, but I have to be kind of stringent on those dates or those times. So unfortunately, I can't do that. But again, I am dropping them, and there's it's okay. They're going to be there's another one that's going to come out probably tomorrow at this point.
So it's usually before class, like it's due before class.
Yep, before class.
Okay, sounds good. Thank you.
All right, thanks, Kevin.
Quick question: where was I supposed to turn in the discussion problem set?
There's no turning for the discussion problem set, just the lab.
Oh, okay, really? Okay, thank you.
Yeah, you're good. You're good.
Okay, I was slightly worried.
You're good. All right. Okay, guys, we will see you guys on Tuesday then.